Hi everyone, welcome back to channel SS Informatica. Here in this session, I just want to explain about indexes, how to create indexes and all index and views. Let's cover. I try to cover indexes first. Indexes is one of the major important topic. Uh, they will ask at least one question from indexes. What are the types of indexes? Have you ever used index? What are the types of index? What is the difference between cluster index, non-cluster index? Like that they will ask. Difference between cluster index, non-cluster index. Once they ask to me. See, let's go to indexes. Here an index is a data structure which can speed up searches on a table if properly implemented. Index is a data structure which can speed up searches on a table if properly implemented. An index can be applied to one or more columns in a table. Indexes are a separate data structure to the table on which they are applied. Indexes take up storage, they occupy storage, right? An index can slow down, insert, update and delete statements because the index also needs to be updated. An index can slow down, insert, update, delete statements because the index also need to be updated, right? Let's see. An index in a database can be linked to an index in a book, right? Not link, it's like an index in a database can be likened to an index in a book, like similar to an index in a book, right? A book index helps you to quickly find what page to uh, find some topic, right? A book index copies a small piece of information that is like topic and then orders it on alphabetically. Each topic has a reference to one or more page numbers in the book. An index in a database references locations in a table rather than pages in a book, right? An index in a database references locations in a table rather than pages in a book. Each topic has a reference to one or more page numbers in the book, right? Let's see. The important thing is to know when it is appropriate to use a certain type of index, right? The important thing is to know when we have to use an appropriate index. They will be just we will cover different types of index, some indexing guidelines also, right? Let's see. But now let's first cover some common terminology, right? Here heap. A heap is a table that does not have a cluster index on it. Let's see some basic topics. Later we will cover types of indexes. Don't worry about cluster, non-cluster and all types. Just remember these terminologies. A heap is a table that does not have a cluster index on it. Table which table does not have a cluster index, that is called heap. Table scan. A table scan is where the SQL engine reads all the rows and columns. A table scan is where the SQL engine reads all the rows and columns. Heap is a table that does not have a cluster index on it. A table scan is where the SQL engine reads all the rows and columns. See. Table scan like an SQL index scan. An index scan is where the SQL engine reads all the rows and all the columns in the index. Table scan is the engine reads all the rows and columns from table, and index scan is that the engine reads all the columns and rows from index, right? Index seek. An index seek uses the index to pinpoint only the rows that are needed to satisfy the query. Index seek. An index seek uses the index to pinpoint only rows that needed to satisfy the query. Cardinality. Cardinality refers to the number of unique values in a column. Cardinality refers unique columns, you know, right? Unique columns. unique values, sorry, not in number of cardinal refers to the number of unique values in a column, means distinct elements in a column, distinct values in a column. You can call it as cardinality. Selectivity is a measure of how much an index can help to narrow the set of specific values in a table. There are two ways it can be expressed. Average selectivity is the cardinality divided by the total number of rows in a table. Selectivity is a measure of how much index can help to narrow the search for specific values. Selectivity of a specific value is the number of rows for a specific value divided by the total number of rows in a table. Number of rows for a specific value divided by the number of rows in a table. Cardinal divided by the total number of rows in a table. Let's see for specific value. See what is average cardinality, average sensitivity. Selectivity is the cardinality divided by the total number of rows in it. What is cardinality? Total number of distinct values is called cardinality. And specific here specific selectivity means for a specific value divided by the number of rows in a table. Let's see with example. Here see we have a table of orders and one of a column called order status. To work out the cardinality, we can write the following query. Right, see, count distinct order status. Count distinct order status as cardinality. It will give distinct. We have to mention distinct. If you didn't mention distinct, if you only mention only count, it will give all the values, total number of values in the total number of rows in the particular column. If you mention distinct, it will give unique values. Distinct means filter out duplicates, unique values. So that distinct values is called cardinality. So you can answer what is cardinality if they ask what is cardinality. The distinct values, the number of distinct values in a column is called cardinality, right? Distinct of order as cardinality from DBO orders. Let's see. Here cardinality 4. Order status. See, order status how it was for closed. Closed is one cardinality, shipped one cardinality, packed one cardinality, open one cardinality. Four distinct elements, four distinct values there, four unique values, right? Closed 2 times, shipped 4 times, packed 1 time, open 3 times. But what overall the distinct elements we call 4, right? Let's see. Selectivity. Average selectivity means, let's see. That cardinality multiplied with 1.0, it's just a bit of a trick to just convert it to a decimal because we will get getting some fractional results also, that's why. So distinct values by total values is called average selectivity. 0.4. So can average selectivity is 0.4. The higher the average selectivity, more uniqueness the values in the column. Higher selectivity is there means higher uniqueness is there. So for instance, the order column has an average selectivity of 1 because it has unique values. Order ID column has selectivity. Higher selectivity is there means higher uniqueness is there, right? So here on comparing to order ID is 10 numbers and 10 divided by 10 means 1. 1 means high uniqueness for order ID column. Let's see a selectivity for value, for particular value. Select count star from orders where order status is equal to closed. I want closed for particular value. I want a particular value. Selectivity for particular value. For closed in order status column, we want selectivity for closed is C. Select count star from orders where order count from where order status is equal to closed into 1 by count star as selectivity for value. See here 0.2. The selectivity for closed from that column is 0.2. Selectivity of a specific value closed is 0.2, and if we if we express this as a percentage, 20, we will say that 20% of the rows have the value called closed, right? And if we look at the table, we can see this. See, we can see this is the case. We have got two rows which have an order status ID closed 2 out of a total of 10 rows equal to 20 percentage. Let's now look at the implications of the selectivity measures when it comes to indexes. How to implement in indexes. When average selectivity is low for a column, then it is often best not to the index that column. If selectivity is low, better to selectivity if selectivity is low, better to avoid the indexing. For example, imagine a column with two possible values, yes or no. Then there are 10,000 rows in the table. Then the selectivity would be 0.00002, right? It's not necessary. The indexing of the column is not necessary. The column had an even distribution. See, 50% of the rows have a value of s and 50% of value of, then this means SQL would need to access the index 5,000 times to find one of the two possible values, right? It accesses the index 5,000 times to value the find one of the two possible values. Accessing the index takes time, and in this case the query optimizer will likely determine it faster to simplify, do a full table scan, and therefore not use the index. It's better to go with full table scan instead of getting into tables index scan, right? Let's see index types and their guidelines. Index types. First index type is like see, right? Yeah, some index guidelines and index types will cover. We'll cover that non-clustered index. A non-clustered index is a regular B plus tree index. A non-clustered index is stored at a different place to the table data. The non-clustered index contains pointers to the location of data. This allows for multiple non-clustered indexes on a single table. This allows for multiple non-clustered indexes on a single table. You can create multiple non-clustered index on a single table. How to create non-clustered index? Create non-clustered index, index name on table, and which columns you want, the 2 columns, the 3 4 columns you want to create one index, you can create. Let's take an example. Create index ix accounts account name on dbo.accounts account name. Here account name column, on account name column we create an index. Okay, let's now have a look at clustered index. A clustered index is an index which physically sorts the table data according to the indexed columns. It sorts the table data according to the index column. Clustered index is an index which sorts the table data according to the indexed column. Table data can be stored in only one way. Therefore, we can only create one clustered index per table. Table data can non-clustered index we can create a number of non-clustered index per table, but for coming to clustered index we can create only one clustered index per table, right? By default, a primary key constraint will also create a cluster index on the primary key column. For example, alter table dbo.accounts add constraint. For just it's a command to add constraint name and primary key and cluster. If required, it is possible to create a cluster index by itself on a column that is not the primary key. For example, like this you can create clustered index name on the table and column name. db order template and as the column on which column you want to lay. Let's see primary key versus cluster index. A primary key constraint is a logical concept. A primary key constraint ensures that the key columns can be used to uniquely identify each row in a table. Right? A cluster index is a physical concept. See, a primary key constraint ensures that key. It's a logical concept. It's a physical concept. A clustered index defines the order that rows in a table. A clustered index defines the order that the rows in a table are stored on disk. It, it does this based on the column specified in the cluster index. A cluster index can even be applied to a column that does not have unique values. Even though unique values even though unique values have not in particular column, you can apply cluster index to a particular column, right? Let's see. However, it's generally recommended to apply the cluster index onto a column that has unique values. Better to go with columns which have unique values. And here, mostly the primary key does not necessarily have to be the same as cluster index. Primary key columns do not necessarily have to be the same as cluster index columns, right? Okay. Should primary key always have a cluster index? It's a question mark. Just to recap, a primary key automatically creates a cluster index if there is no other existing cluster index on the table. A primary key automatically creates a cluster index if there is no other existing cluster index on the table. In most situations, it is best to just leave it on the default and have the primary key create an associated cluster index. In most situations, it is better to just leave it on the default and have the primary key create an associated cluster index. There are some situations where we might put a cluster index on different column on the primary key. If there is some alternate key that is more frequently used in queries, the primary key has a large key width. This is because the clustered key values get replicated in every one of the non-clustered index on the same table. See, one more time, the primary key has a large key width. This is because the clustered key values get replicated in every one of the non-clustered indexes on the same table, right? Let's see. Okay, let's see unique indexes. Cluster index have completed non-cluster index. Just unique go to unique index, and unique index ensures that a column can only contain unique index. Unique means definitely unique index means definitely that column should contain unique values. By default in SQL Server, when either a unique constraint or primary constraint is created, then a corresponding unique index is also created. So like primary key constraint, if unique constraint is there in the table, it will automatically corresponding unique index is also created. A unique constraint will automatically create a corresponding non-cluster constraint. See, primary key constraint creates a clustered index automatically. Your unique constraint create a non-clustered index automatically. A primary, right? This is a difference. Unique index can also be created by itself, like by query, by using query you can create unique index name on the table and the columns in braces. We have to mention that columns in the braces, right? Both contain columns to be unique. In addition, when we define a unique constraint, SQL Server automatically create a unique index. A common question people have is, doesn't matter whether I use a unique constraint or just do a unique index by itself. The answer is that it is fine to use every approach, but if the main purpose of the unique valid column is that it is a column to be searched on and queries and could benefit from performances, then I would recommend adding a unique index to it, right? However, if there is a business rule which says that this column must be unique, then use a unique constraint. The goal here is to make the intent purpose of the column more obvious when someone is looking at, right? Let's take a look at another type of index which is called a filtered index. A filtered index is a type of non-clustered index where only sum of rows are indexed based on some condition. Because only a portion of rows are indexed, this can save on space and improve query performance. Filter indexes are useful on columns that have a lot of nulls. Mostly filter index useful that the columns have a lot of nulls. Filter indexes are useful on columns that have a lot of nulls. Filter indexes are also useful if you often query for a value that makes up a small portion of the total rows in a table. Filter indexes are also useful if you often query for a value that makes up a small portion of the total rows in a table. See, create index name on table columns where condition you can give. Okay. Based on where condition, it will called as filter index. Right? Just example, termination date is null. Here the index where termination date is null, it will give where the termination date is null. Let's see, we had some cardinality and selectivity in the last session and previously. However, over time we can expect most orders to be updated to a status of closed. For example, see here. So now we have a lot more closed orders. However, when we write queries, we are most likely going to be select only the orders that are not closed, right? So most of the time we are only interested in a well-defined subset of rows where order status is like not closed. Therefore, this is a situation where filtered index might be useful, where we just index the values, right? Where order status does not equal closed, and see, create a filtered index. Create index name on the table and the columns where order status not equal to closed. Right, not equal to closed means remaining shipped and open we will get, right? General indexing guidelines: avoid over indexing heavily updated tables, right? And we make a change to the table data, then the index also needs to be maintained. Keep indexes narrow with a few columns as is required, right? You can create many index on a table that is seldom updated. This is because for a table that is seldom updated, it's not so much of a concern that indexes will slow down. Slow down, insert, update or delete statements, because this does not happen often. Indexing small tables that are likely to stay small is often not necessary to do, right? Consider indexing foreign key columns. Consider indexing foreign key columns. Typically, we join tables by join the primary key of one table to foreign key of another table, right? The primary key column automatically gets given a unique index, but SQL Server does not create any automatic index on the foreign key column. Oftentimes, it is useful to add an index on the foreign key column, and it can improve the performance of queries that join on the foreign key column. Generally, we just add a standard non-clustered index on a foreign key column. Consider filter index to help optimize queries that return a well-defined subset of rows from a large table. Let's see couple of examples. Okay, let's now look at some guidelines of clustered indexes also. With few exceptions, it is best to put a cluster index on every table, right? As previously mentioned, in most cases you can just let the primary key constraint automatically create cluster index, right? Create a cluster index for you by leaving it on the default for primary key constraint. Ideally the cluster index should be put on a column that is uniquely not now narrow in size and typically exists sequentially. Let's take a look at an example. See, it's a so here we have a table of products. We have a column called product name of dollar type, that 50 dollar type ID. We have a column called global ID. Global ID, it's an identifier constraint will be given, unique identifier constraint will be given. See, see the global ID would have looked something like this. So now we have sequential values for the global ID. However, global ID is still a wide sized column. If you put a cluster index on the global ID column, then the wide those values get replicated in every one of the non-cluster index that we put on the same table, right? Therefore this could slow down performance. A better candidate column for a cluster index is if we add on an integer column called some product ID and give it the identity property, which so that product ID is better to use as the cluster index, as it has all four of the ideal qualities. I would also recommend making product ID the key primary key column as well, right? See, in addition the product ID is likely to be queried in a sequential search. For example, we might have a where product ID between 500 600. This type of query would benefit for a clustered index on the product ID because with a cluster index, the rows are stored in the stored order. That column. Okay. See you in the next lecture. Types of indexes, composite, and some more part 2. Indexes types part 2, composite and included indexes. A composite index is where multiple columns are specified for the index key, right? Here create index on customer's first name last name. Multiple columns are specified for the index key. A query can only use a composite index to do an index seek if the where clause of the query has at least a leftmost column. In a composite index, it is usually best to choose the column that has a higher degree of uniqueness, higher selectivity as the leftmost column. Okay, let's take a sample example. Query C. We have table of customers. Firstly, note that there is a primary key at a cluster index. Let's put a composite non-cluster index on the table. Composite non-cluster index, create index name on customer's first name last name. I have just written a create index. Let's see. Also recall that the cluster index values are replicated in every non-cluster index, right? Therefore, this non-cluster index also includes the customer ID key values, and that's because customer ID is our clustered key. Okay, let's say we write the following query: select customer ID, first name, last name, where customers from customers where first name is equal to Elisa and last name is equal to Jones. For this query, the query optimizer can use the composite index to do an index seek, right? In this case, returning one row of customer ID number 3. Note that even if we switch the order of the conditions in the where clause, it will still do that exact same thing, right? See, for example, so now we have specified last name equals Jones as the first condition, and then we have first name is equal to Elias as the second condition. We'll be able to use index seek because we still include the leading column first name in the where clause. See, so again we get we get one row. See, we get one row return. See, okay, let's clear all this. Alright, let's now do the following query. So now we have one condition in where clause where first name equals Elisa. For this query, query optimizer can use the composite index to do an index seek because we are still filtering on the leading leftmost column first name, so we can still the composite index, and it will go straight to any row where first name equals Elisa. In this case we get one row. Let's now filter only last name column. Now we just have last name equals to Jones. For this query, the query optimizer cannot use the composite index to do an index seek because the leading column first name has not been specified in the where clause. Instead of an index seek, this query will likely to do an index scan. So it will scan the whole index to find the qualifying rows. Okay, let's clear this. Now we will try to following query. See, in this case we get one row written from this query, and this query is very similar to the first row. In this case we get one. See, in this case we get one row written from this query, and this query is very similar to the first row. We did however notice that the query includes an extra column in the select clause, that is the city column. So we are selecting an additional column that is not included in the composite index. So this means that the query cannot do an index seek on the non-cluster index because the city column is not involved in the included in the index. In this case, what we can do is we can change the index to include the city column, but we do so by using the include clause, right? See, therefore we can drop this index. So now we are creating a composite non-cluster index on the first name last name column like before. See, however this time we also have the keyword include. See, same include, and then after that with parentheses we have to mention, specify the column that we want to include. In this case the column is city. So in other words, we are including the non-key column city in this index. See, This means that for this query, the query optimizer can do an index seek. This is because we included city as a additional column in the index. All right, let's go through some indexes. We included columns in a see. We included columns in a bit more detail. That include column allows to include non-key columns in a non-clustered index, right? Uh, this can be useful for queries that include non-key columns in the select clause. Index key columns are stored at all levels of the index structures, whereas the non-key columns are stored only at the lower level. Right, this means the specifying a column in an included column rather than as part of the index key will have a lower storage cost, right? See, include columns can also be data types that are not allowed in index columns, for example XML or ARCA data types. And if we look at the syntax, so the first set of columns, see, create non-cluster index name on table, set a table column 1 column 2 include column 3 column 4, like that. Okay, let's now just summarize a few key points. We say that an index covers the query if the index contains all the columns referenced by a particular query, right? See, if a query is filtering on multiple columns in the where class, that it might benefit from a composite index on these columns. If a query is selecting additional columns which are not filtered on, then it might benefit from putting these columns in a include clause on the non-clustered index, right? Let's see, it's not required. Let's see later a few see some challenges, few challenges and indexes later.